Hey everyone, welcome back to the channel. I have great news this episode. I think we have the hardware side done. Here I have my custom PCB board. I made it into Metro Shield format, so this will stack on top of the ESP32 board as well as the GPS Shield, similar to what we have here with Mustang's project. He made it stackable, and that's what I did. We've come a long ways. First, I wanted to talk about, this is actually my second iteration of my custom PCB. The first one is here, very similar. I have my power section, my control section with the relays, and then a speed control section. This is my second version because I could not get the digipot to work correctly, the speed control. I'm not 100% sure what's going on there. I did look at the data sheet, and there's a formula in there that talks about the input voltage, or the voltage to power the chip, should be needs to be in a certain tolerance of the logic pins. The ESP32 uses logic pins. The SCL and SDA pins are at 3.3 volts. We were trying to feed the chip 3.9 volts. According to the data sheet, it should still work, but for some reason I wasn't able to control the voltage. It was always stuck at like 2.61. I have it in my notes somewhere. So this first version was a failure. I had to look at how to redesign the speed control, but this first iteration I was able to test the power circuit, and which is where we took that 12 volts and dropped it down to the 6 or 7 volts. So the voltage regulator on the ESP32 didn't have as much heat. And then I also tried the relay section, which I got to work as well. So the second iteration, I completely changed from a digipot to a DAC with op amp. So I'm using the 3.3 volts from the ESP32 and using the DAC to control that voltage from 0 to 3.3 volts, and then using the op amp to bump it up to that 3.9 volt range so I can get full range of the voltage and speed control. So we have it here. I'm going to bring this on over to, I'm going to show you how I designed this in KiCad. It is a freeware schematic and PCB design software. So yeah, great news. We are on track. We have the hardware side, I think, close to being completely done. Now I really need to get on the water and test it out and start writing the software side of things. Hey guys, I'm here in KiCad. I'm not going to teach you too much about the program. You can go in and YouTube other tutorial videos, things like that, to figure out how to draw things. But the way I did this was I broke it up into different sections, and starting off with the ESP32 Metro S2, you can go into the program. There is a template to bring this in where it'll give you these pinouts here, and then I added in these flags of the GPIO pins based off the S2. These GPIO pins actually change for the newer S3 version, so you'll have to check the pinouts on the Adafruit website for that. The next section I have is the input section, which are the motor inputs. So these are the 7 wires from the motor input control. We have our yellow wire, green wire for steering, and then our 12 volt rail. We'll use that in our circuits. Our ground, our 3.9 volts for speed control, as well as the output for speed, which is the brown wire, and then turning on the main motor on and off, which is the white wire. Then I went into what I'll call the control section, which is our on and off. Next, we'll go into our what I'll call the control section, which is our on and off and our steering left and right. I use the same circuit for each one of these. What I'm doing here is I'm taking my GPIO pin from the ESP32, going through a gate resistor. And this gate resistor limits peak current and improves our electromagnetic interference. We also have a pull down resistor, which is this R8 at 10,000 kiloohms or 10 kiloohms. And what this does is it stops the gate voltage from having a floating or undefined gate voltage, and prevents our gate glitches and chatter for the MOSFET here. One issue that you might run into if you don't have this is that when you power on the ESP32, when it goes through while it's powering up and initializing everything, you might get some chatter here. This should prevent that. Next, we have our MOSFET here. Again, this acts as our switch to use our voltage from our GPIO pin to turn on this switch to activate our relay and limit our current that we're pulling from the ESP32. We're using our 12-volt rail from the motor for the relay coils. And for the relay, we're using that Texas Instruments TX2 12-volt version. And that should reduce our voltage here, or the amount of current it takes to activate this relay. Other things that we added to the circuit are a flyback diode, this SS36. What this does is protect our relay by when the relay de-energizes, it might have some extra current or some back current, and this flyback diode will protect our relay. We also have our TVS diode here, this SMA J15A, and this will protect our external power supply, that 12-volt rail, accidental overvoltage, and power supply spikes. These capacitors also will stabilize our voltage, reduce those power supply spikes and dips, so we added this here as well. The only difference between the three relays is we're only using a single side for the on and off, and then for the control left and right, we have to use the two latches, but everything else is the same. This is our version 1. So in this speed control, I was using that digipot. We're using the AD5273, and this is the diagram I came up with. Wiper was the brown wire. We're turning on the chip with our 3.9 volts. SCL and SDA are our logic pin controls. One side of the resistor was 3.9 and the other side was ground. And then I can't remember what AD0 is for, but we fed it 3.3 volts. Looking at the data sheet, I think it should still work. They had this here that might be the issue of why I couldn't get to work. It says that our minimum voltage should be 3.9, which is our VDD times 0.7. So our input, our logic pins should have a minimum of 2.73 volts, which we get with the ESP32 with the logic pins being 3.3 volts. I'm not 100% sure why it wasn't working. I would like to go back and try this again, maybe buying a breakout board for the SOIC 8 package chip, so I can get a breakout board, solder it to that breakout board, and play around with it more. It would be much easier if this type of device was in the DIP package where I could just put on a breadboard and work with it, but they don't sell it in that type of package. We did get it to work with that other digipot using a kind of a different control interface. Some other things that we might be able to do is buying a digipot using the SPI controls versus the I2C control. Something to think about, and maybe we'll go back and look at it if we're really that curious. Lastly, we have our buck converter, where we take that 12-volt rail from our motor and try to decrease the voltage to something where we're not having to overload that. we're not having to overload the power regulator on the ESP32. So in this data sheet for the buck converter, they have a power design, a web bench power designer on the Texas Instrument website. You can go to it and you can give it the information that you want to give it. For us was the 12 volts in VN. We want, let's just say 6 volts out. And I just kept the current the same. And then down here, you can do your design considerations or different parameters. But I went ahead and did this. It came out with a circuit, which you can pick one. The one I chose was this one here, and it gives you all the parts. You can adjust the voltage by changing these two resistors, the RFBT and the RFBB. In the data sheet, it gives you a formula in there that tells you how to come up with voltage changing those two resistor values. And I wrote those in over here. In my testing, at this point it should actually be 1, so you can adjust that accordingly. Then I added some extra diodes in the circuit for protection as well. So that was version 1. And I will also show you the PCB of that as well. So you can go in here, import all the, you just do an import and it'll bring in all your parts. And then you can create a shield here as well. So the way I broke this up is, again, 3 portions. I have my power section down here on the bottom. We have our control section here, and then we have our speed control up here. We also add in port for our I2C for our compasses, and then some extra ports here, which are for our menu buttons, and then one for our battery charger, which is using 5 volts from our ESP32. So that was version 1. I'm going to show you version 2 real quick. Not much has changed. The main thing that changed in that is using our digital analog plus RC filter and op amp to produce our 0 to 3.9 volts for our speed control. I came up with this circuit by using the data sheets. For our digital analog converter, we have this circuit here, and I used that to come up with it. And then also with the op amp, we have their circuit here for a low pass filter here. And then you have your formula of this here to come out and figure out what resistor values we need for RF and RG to come up with that for 3.9 volts. So I wrote that here. V out equals V in, 1 plus our resistor here, R18, and our resistor down here, which is R19. So we have a V out of 0 to 3.894 volts, which is close enough to that 3.9 volts. In our prototype, we did figure out that we don't need the full 3.9 volts to get to full speed. I think it was around 3.7.5 volts or something like that. I'd have to check my notes, but we don't need the full 3.9, but it's good to still have that range. What's nice about using this speed circuit is that we're using a 12-bit DAC, so that means that we have 2 to the 12th, 4,096 steps that we can actually control the voltage. We don't need anything that fine, but it's still nice to have that kind of control. One other thing I changed was I changed this the buck converter to SOIC package versus the QNFR package. That was just based off of a little difficulty soldering the QFN package. Those type of packages are probably better used with a hot air station, which I have one. I bought it, I think, last year to try to repair something, but I'm not too practiced in it and not too comfortable, so I went with, in the second version, I went with the SOIC package. I still needed to use the hot air station to solder the bottom, which is the ground, but it was much easier to be sure that everything was connected. One other thing that I did in version 2 is I added test points along the PCB board, especially in this section here where I could make sure that I had the right connections and voltage. I know in that first version when I tried to, where I didn't have test points, I tried to check my voltages in places, and I actually shorted the board out a couple times, and it would burn out some of the traces, and it was kind of a disaster. So here's the schematic, or the PCB board design. Again, not much changed. The only thing that really changed was this speed control section. You can see it's a little bit more complicated than the original design. So after I designed the PCB boards, drew the schematics on all that, the program has a plugin for PCB Way, which is the company that I ordered the PCB boards. And they're relatively cheap. And you just click the button and it'll basically populate everything for you. It's relatively cheap. I kept everything at default, and as you can see, it's pretty cheap. I mean, $12 for plus shipping for 5 boards, which is plenty. And you can change the color in here as well. So as you can see, or as you see, I used white for my boards. So that was the easy process. KiCad made it pretty simple. It was just learning how to do some of the design. PCB board was kind of tough just to try to make everything uniform, but it was still fun to play with and learn. All right, so let's look at our PCB board, all soldered up. Again, we have our speed control section over here. See our op amp and DAC are over here. Some resistors, capacitors, things like that. We have our control section. This is the bottom side. And then we have our power section here. And then this is our buck converter here. Let's look at the top side. We have our inputs. Inputs here. And as I said, I probably could have got away with just 2 of the 3 3-pin inputs. We're not using the 3.9 volts since we're using the 3.3 from ESP32 for our speed. We have our control section, our relays here, 3 relays. These 3 capacitors for voltage stabilization for each one of these relays. We have some inputs over here. For one is for the battery charger, and then our extra buttons on the console, and then our I2C input port for the 2 compasses that we'll use in the program. We designed this as a shield, so it will stack on top of our ESP32 and our GPS shield module as well. So that's how we got down to our designing our PCB, our circuits, and our prototype. I tested a lot of these circuits on our breadboard prototype. I did also have a circuit for this as well and tested it, and it worked fine. That's why I decided to go this direction. So there you have it. There is the design in KiCad, the custom PCB. Got it from custom PCB. I got it from PCB Way. There is a plugin in the KiCad software where once you design your PCB, you can click a button and it will bring up the web page and have the order for you. I ordered 5 of these. It came out to about $1 a piece for the board, plus another, I think, $6 or $7 in shipping. So it's relatively cheap. I have to put together a parts spreadsheet so we can figure out what the total price was for the hardware side, but that shouldn't take too long. I ordered most of my parts from DigiKey or from Amazon. So the hardware side was really fun to play around with, to design, going from that original Minn Kota foot control here to variations of different hand controls, to our prototype, and then our final PCB. Next, I just really need to get out on the water, test it out, and start writing the different functions and different features that we want in the software side of things. I appreciate you guys tuning in. I would still love to get some comments. We've had 6 or 7 videos now, no comments, so I'm not 100% sure where I should go or what direction I should go for the software side of things. I'm going to do the basic functions of manual control, navigation, or kind of a hold heading. Maybe we can add some waypoints there, and then our spot lock function, which is really probably the most important feature for me. Hey guys, in the garage. Just want to do a little tease here. I did tell you guys I wasn't really going to jump ahead and do all these different things all at different times, but I got excited and worked on the software side and trying to get everything to work, but I also wanted to show you guys everything that works with the hardware. I did say I wasn't really going to modify the motor. I did end up taking off the head cover, taking the compass that was already built in to the head, and put in the compass that is part of our ESP32. So we have one for the motor head, so we can figure out what our heading is from the motor, and then we have one that I mounted underneath. I mounted one under the bow here that shows the boat heading, and we have it connected to this, which is connected to our console and to our PCB board. I also wired a power on button here and power it up. As you can see, this will turn on because it's hooked up to the battery. I started doing some programming. We have manual mode here. We already worked on this several times with the other hand controls and other iterations, so that's not that big of a deal. We have our boat heading and motor heading readings, and then our lat and longitude readings as well. And then we have our hand controller here. And then we'll turn it on to trigger the battery. We turn on the motor. Speed works. I'm not gonna go full speed. I'm not gonna put the motor down so you can hear, but you can hear it trying to turn left and right. It does work. The GPS function works as well. I'm not gonna show you the GPS, my coordinates, just for my privacy, but it does work. And I just really need to get on the water and start troubleshooting the software side of everything, but it looks like I have the hardware working pretty well so far. So that's the tease. Again, thanks again. Like, subscribe, and I'll see you in the next episode.